Welcome to the final lesson of the series. Concurrency is where everything we've built up so far really pays off. In most programming languages, writing code that runs on multiple threads is a minefield. Data races, where two threads touch the same memory simultaneously and produce unpredictable results. Deadlocks, where threads block each other forever. Heisenbugs, where the bug only appears occasionally, under timing you can't reproduce. Debugging concurrent code in C or Java or Python is often the hardest work a programmer ever does. Rust's designers made a bold claim. If your code compiles, it is free of data races. They call this fearless concurrency, and it is not marketing. It's a direct consequence of the ownership and borrowing rules you already know. The same rules that prevent you from having two mutable references to a value in single-threaded code also prevent you from sharing mutable state unsafely across threads. In this lesson, we'll spawn threads, pass data between them with channels, share data with mutex, make sharing safe across threads with Arc, and understand the two marker traits send and sync that make all of this work. By the end, you'll have the full picture of Rust's concurrency story. Starting a thread in Rust is straightforward. The standard library's thread module provides a function called spawn. You call thread : spawn, pass it a closure, and the closure runs on a new operating system thread in parallel with the rest of your program. Spawn returns a handle, a join handle, that represents the thread. You can use this handle to wait for the thread to finish by calling .join. Join blocks the calling thread until the spawned thread completes and returns whatever value the thread's closure produced. If you don't join a spawned thread, the main thread might exit before it finishes, and when the main thread exits, the whole process exits, killing any remaining threads. This is an important subtlety. It's your job, as the programmer, to coordinate which threads run, which you wait for, and in what order. In the example on screen, we spawn a thread that prints some numbers with small delays. The main thread immediately calls join, so it waits for the spawned thread to finish before continuing. Without that join, the main thread might fall through to the end of main and exit before the spawned thread got a chance to print anything. Threads in Rust are real OS threads. They're preemptively scheduled, they can run on different cores, and they have the usual costs and benefits of OS threads in any language. When a thread closure captures a variable from its surrounding scope, that variable is borrowed by default, which creates a problem. The compiler can't tell how long the borrow needs to last, since the thread might run indefinitely. It also can't tell whether the original owner will still be valid when the thread actually uses the borrowed data. Rather than guess, the compiler refuses. The solution is simple. Add the move keyword before the closure's opening pipe. Move transfers ownership of every captured variable into the closure. After the spawn, the thread fully owns those values and can use them independently of what the main thread is doing. The main thread can't use them anymore. They've been moved. In the example, we have a vector we want the spawned thread to iterate over. Without move, the compiler refuses to compile. With move, ownership transfers, and the thread can work with the vector for as long as it runs. You'll see the move keyword on nearly every thread : spawn call in real Rust code. It's the idiomatic way to give a thread exclusive access to data it needs. One of the simplest and safest ways for threads to communicate is message passing. Rust's standard library provides this through the mpsc module, short for multi-producer, single consumer. Calling mpsc : channel returns a pair, a sender and a receiver. The sender can be cloned any number of times to create multiple producers, each of which can send values into the channel. The receiver, of which there is only one, reads values out in the order they were sent. In the example, we create a channel, then spawn 3 threads. Each thread gets its own clone of the sender, so they're all producers. Each sends a unique message. The receiver, which stays on the main thread, iterates over the incoming messages until all senders have been dropped. Notice we call drop on the original TX before the loop. Otherwise, the main thread's own sender would keep the channel alive forever, and the for loop would never end. This design, share by communication, not communication by sharing, is inspired by the Go programming language and works beautifully with Rust's ownership model. Once a value is sent through a channel, it's been moved out of the sender's possession, so there's no risk of the sender and receiver both modifying it. Channels are ideal when threads have clear pipelines of work or when you want to fan work out to a pool of workers. Sometimes you really do need shared state, not message passing, a global counter, a cache, a shared configuration. For these cases, Rust gives you mutex, short for mutual exclusion. Mutex is a classic synchronization primitive, present in every concurrent programming library in existence. But Rust's version has a twist. In most languages, a mutex and the data it protects are two separate things, and it's up to you to remember to always lock the mutex before touching the data. Forget to lock, and the data race you were trying to prevent happens anyway. In Rust, a mutex wraps the value directly. The only way to access the inner value is to acquire the lock with .lock, which returns a guard. The guard gives you access to the value. When the guard goes out of scope, the lock is automatically released via the drop trait we saw last lesson. You literally cannot access the data without holding the lock because there's no way to reach the data except through the guard. And you can't forget to unlock because the guard's destructor handles that. Those are both entire bug classes that plague mutex usage in other languages, eliminated by the type system. In the example, we wrap an integer in a mutex, lock it briefly to change the value, and let the guard drop to release. To share a mutex across multiple threads, you need a thread-safe shared owner. RC from the last lesson won't work. RC uses a non-atomic counter, which would race between threads and produce undefined behavior. The compiler refuses to let you use RC across threads for exactly this reason. That's where Arc comes in, the atomic counterpart. Arc works just like RC. You call Arc clone to create new owners, you drop them to decrement, but the counter uses atomic operations that are safe across threads. The canonical pattern you'll see in real Rust code whenever you want shared mutable state across threads is Arc wrapping a mutex wrapping your data. Arc of mutex of T clone the arc to give each thread its own handle. Inside each thread, lock the mutex to read or write. Trust the compiler and the runtime to catch any misuse. The example spawns 10 threads, each of which increments a shared counter by 1. After joining them all, we read the final value, which is exactly 10, reliably, across any run of the program. This is the kind of simple concurrent pattern that goes terribly wrong in languages without Rust's guarantees. Here, it's a textbook example that just works. Under the hood, two marker traits in the standard library are what make all of this work. They're called send and sync. Send means a type is safe to transfer to another thread. If T is send, then you can move a T from one thread to another. Sync means a type is safe to share between threads. Roughly, if $T is send, then T is sync. Most types implement both automatically. The compiler figures it out structurally. If all your fields are send, your type is send. If all your fields are sync, your type is sync. Some types deliberately don't implement these. RC isn't send because its non-atomic counter would race across threads. refcell isn't sync because its internal borrow tracking isn't safe against concurrent access. If you try to send one of these across a thread boundary, the compiler stops you, often with a helpful error message suggesting the thread-safe alternative. You rarely interact with send and sync directly in application code. They're the invisible scaffolding that supports thread, spawn, mutex, arc, and every other concurrency primitive. But knowing they exist and knowing what they mean is deeply satisfying. Rust's fearless concurrency is ultimately a story about these two traits, applied consistently everywhere. That's concurrency in Rust, and that's the whole series. 14 lessons, from the first let binding all the way to fearless multi-threaded programming. You now have the entire core language in your head. The next step is to build something real with it. Pick a problem you care about, start a new cargo project, and fight the borrow checker until it bends to your will. Thank you for watching, and happy coding.